let me tell you something that might sound strange at first. Physics, the most successful science humanity has ever built, the one that put people on the moon, that lets you hold a glowing screen in your hand connected to every other screen on the planet, that predicted the existence of particles decades before anyone found them. Physics, for all of that breathtaking success, still cannot answer some of the most basic questions you could ask about the universe you're lying in right now. And I don't mean obscure, abstract puzzles that only matter to someone scribbling equations on a chalkboard at 3 a.m, although those exist too. I mean questions like, what is most of the universe actually made of? Why does time move forward and not backward? Why is there something rather than nothing? These aren't fringe curiosities. These are gaping holes in our understanding, and the smartest people alive are staring into them right now, working late, arguing with each other, occasionally having the kind of quiet, terrifying realization that everything they thought they knew might need to be rebuilt from scratch. And here's the thing. The story of how we got here, how we arrived at this particular set of unsolved mysteries, is itself one of the great dramas of human thought. Because every unanswered question in physics today is the child of an answered one. Someone figured something out, and that triumph opened a door, and behind that door was a deeper, stranger problem that nobody saw coming. That's the pattern, over and over, for about 400 years. It's beautiful and maddening in equal measure, and tonight we're going to walk through it slowly, starting from the very beginning, from the moment people first started asking these kinds of questions in a way that could actually lead somewhere. So let's go back, way back, to a time before physics even had a name. For most of human history, the big questions about the universe, why things fall, what the stars are, why the seasons change, those were answered by mythology, by theology, by philosophy. And honestly, some of those answers were remarkably sophisticated. Aristotle, around 350 BC, built an entire system of natural philosophy that explained motion, matter, the heavens, the elements. He said heavy things fall because they're seeking their natural place, which is the center of the earth. Light things, like fire and smoke, rise because their natural place is up, near the celestial sphere. It sounds quaint now, but think about what he was doing. He was trying to build a unified explanation for why things move the way they do, and his framework held together well enough that people believed it for nearly 2,000 years. 2,000 years. That's not because people were stupid. It's because Aristotle's system was internally consistent. It matched everyday observation reasonably well, and nobody had a better method for testing it. The method, that's what changed everything. And the person most associated with that change, the one who cracked open the door to modern physics, was a stubborn, brilliant, occasionally insufferable Italian named Galileo Galilei. Born in Pisa in 1564, Galileo did something that sounds simple, but was genuinely revolutionary. He insisted on measuring things, not just thinking about them, not just reasoning from first principles the way Aristotle did, but actually setting up experiments, timing how long things took, counting, comparing. He rolled balls down inclined planes and timed their descent using his own pulse, because accurate clocks didn't really exist yet. Think about that. Using the beating of your own heart to measure the acceleration of gravity. And what he found contradicted Aristotle directly. Heavy things and light things, if you account for air resistance, fall at the same rate. The speed of a falling object doesn't depend on its weight. That was shocking. It meant the entire Aristotelian framework for motion was wrong, or at least deeply incomplete. Now, Galileo gets a lot of credit, and he deserves it, but he wasn't working in a vacuum. There were others. Kepler in Prague, meticulously analyzing Tycho Brahe's astronomical data and discovering that planets move in ellipses, not perfect circles. That was another blow to the old system, because the ancient Greeks had been deeply committed to circular motion as the natural, perfect form of celestial movement. Kepler showed that nature didn't care about human ideas of perfection. The orbits were squashed slightly but measurably, and Kepler figured out the mathematical laws governing those orbits. His 3 laws of planetary motion, published between 1609 and 1619, without really understanding why they were true. He knew the how. He could predict where Mars would be 6 months from now with remarkable accuracy. But the why, that was still missing. And this is where Isaac Newton enters the story. And honestly, it's hard to overstate what Newton did. Born on Christmas Day, 1642, in a small manor house in Lincolnshire, England, the same year Galileo died, which feels almost too poetic to be true. Newton was difficult, secretive, prone to feuds, and possibly the most powerful scientific mind that has ever existed. What Newton did, in his Principia Mathematica, published in 1687, was unify everything. Galileo's falling bodies, Kepler's planetary orbits, the tides, the motion of comets, the shape of the Earth itself, all of it explained by a single set of laws, 3 laws of motion and 1 law of universal gravitation. Every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. That's it. That one statement, expressed mathematically, explained why apples fall and why the moon orbits and why the tides rise and fall. The same force, the same equation, everywhere. Let that sink in for a moment. Before Newton, there was no reason to think that the rules governing things on Earth had anything to do with the rules governing things in the sky. The heavens and the earth were considered fundamentally different realms. Newton demolished that wall. He showed that the universe runs on the same physics everywhere, and that physics could be written in the language of mathematics. That was the birth of physics as we know it, and it was so successful, so spectacularly, overwhelmingly successful, that for the next 2 centuries, many people believed, with some justification, that Newton had essentially solved the universe. There were details to work out, sure, but the fundamental framework was in place. The machine was understood. You just had to do the calculations, and the calculations worked. They worked astonishingly well. Engineers used Newtonian mechanics to build bridges, design cannons, predict eclipses to the second. When astronomers noticed that Uranus wasn't quite following the path Newton's equations predicted, 2 mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently calculated that there must be another planet out there, tugging on Uranus with its gravity. They told astronomers where to point their telescopes, and in 1846, there it was. Neptune, a planet discovered not by looking at the sky, but by doing math on paper. That's the power of Newtonian physics. It could tell you where to find a planet you'd never seen. So you can understand why, by the late 1800s, there was a widespread feeling, not universal, but widespread, that physics was essentially complete. The famous story, which may be somewhat apocryphal, is that the physicist Lord Kelvin declared around 1900 that there was nothing new to be discovered in physics, that all that remained was more and more precise measurement. Whether or not he said exactly that, the sentiment was real. The Newtonian framework, extended by Maxwell's equations for electromagnetism in the 1860s, and the laws of thermodynamics developed throughout the 19th century, seemed to cover everything. You had mechanics for motion, electromagnetism for light and electricity and magnetism, and thermodynamics for heat and energy. 3 pillars, a complete description of nature. Except it wasn't complete. And the cracks were already showing, right there at the turn of the 20th century, even as people were declaring victory. There were a handful of small, nagging problems, experimental results that didn't quite fit. And here's what's fascinating. These weren't obscure anomalies buried in some specialist journal. They were well-known puzzles that the best physicists in the world were actively worrying about. Lord Kelvin himself, in a famous lecture in 1900, actually referred to 2 clouds on the horizon of physics, 2 unresolved problems that troubled the otherwise clear sky of classical theory. The first cloud was the failure to detect the luminiferous ether, the invisible medium that everyone assumed light waves must travel through, the way sound waves travel through air. The Michelson-Morley experiment in 1887 had tried to measure the Earth's motion through this ether, and found nothing. No ether wind. No difference in the speed of light, regardless of which direction you measured it. That was deeply weird, and nobody could explain it. The second cloud was something called the ultraviolet catastrophe, which is a wonderfully dramatic name for a mathematical problem. Classical physics predicted that a hot object, like say the walls of an oven, should radiate infinite energy at high frequencies. Obviously it doesn't. You can stand near an oven without being vaporized by an infinite blast of ultraviolet radiation. But the equation said it should happen, and nobody could figure out where the math went wrong. These 2 little clouds. That's all they seem to be. Minor issues to clean up. But here's the kicker. Those 2 clouds didn't get cleaned up. They exploded. The first one led to Einstein's special theory of relativity in 1905, which completely overturned our understanding of space and time. The second one led to quantum mechanics, which completely overturned our understanding of matter and energy at the smallest scales. The 2 greatest revolutions in the history of physics, both born from problems that people initially thought were minor, both revealing that the Newtonian universe, for all its glory, was just an approximation, a spectacularly good approximation for everyday life, but fundamentally, deeply incomplete when you pushed it to extremes of speed, gravity, or size. And that's the pattern I want you to hold in your mind tonight. The pattern of physics. You solve a problem, and the solution reveals a deeper problem you didn't know existed. You build a framework that works beautifully, and then you discover the edges where it breaks down, and at those edges, the real questions live. The questions physics still cannot answer today, the ones we're going to explore together. They live at exactly those edges, at the boundary between general relativity and quantum mechanics, at the threshold of the very large and the very small, in the gap between what our equations predict and what we actually observe when we look at the sky. So let me take you to the first of those edges, the one that might be the most unsettling of all, because it touches something you experience every single moment of your life, something so fundamental that you probably never think to question it. I'm talking about time. Specifically, I'm talking about the direction of time. Why it flows the way it does, always forward, never backward, carrying you relentlessly from one moment to the next. You'd think physics would have a clear answer for that. You'd think, after 400 years, someone would have nailed down why yesterday is different from tomorrow. But here's what's genuinely strange. The fundamental laws of physics, almost all of them, work exactly the same, whether time runs forward or backward. If you filmed a billiard ball bouncing off a wall and played the film in reverse, Both versions would obey Newton's laws perfectly. There's nothing in the equations that prefers one direction over the other. The laws are, as physicists say, time symmetric, and yet your coffee cools. Eggs break but don't unbreak. You remember the past but not the future. The universe seems to have a very clear preference for one direction of time, and the deepest laws of physics don't explain why. This is called the arrow of time problem, and it has haunted physicists since the 19th century, since a quiet, melancholic Austrian named Ludwig Boltzmann first tried to explain it using the brand new science of statistical mechanics. Boltzmann's story is one of the most heartbreaking in all of science, and it begins in Vienna in the 1870s, in a world that wasn't ready for what he had to say. He was trying to explain something that seemed obvious, that heat flows from hot to cold, that disorder increases, that things fall apart, using the mathematics of atoms and probability. And the thing is, almost nobody believed in atoms yet. Not really, not as actual physical objects. Many of the most respected physicists and philosophers of his time considered atoms to be a useful fiction, a mathematical convenience, nothing more. And Boltzmann was building his entire life's work on the assumption that they were real, that they were tiny, indivisible particles bouncing around, colliding, exchanging energy, and that the behavior of trillions upon trillions of them, taken together, could explain everything we observe about heat, pressure, temperature, the way steam engines work, the way ice melts, all of it. And he wasn't just hand-waving. Boltzmann was a formidable mathematician. He developed what's now called the Boltzmann equation, published in 1872, which describes how the distribution of velocities among gas molecules evolves over time. It's a beautiful piece of work, dense and rigorous, and buried within it was something genuinely profound. A quantity he called H, which he showed always decreases over time as a gas approaches equilibrium. This was his attempt to derive the second law of thermodynamics, the law that says entropy always increases, from the mechanics of individual particles. He was trying to show that the irreversibility we see in everyday life, the fact that heat flows one way, that things mix but don't unmix, that your coffee cools but never spontaneously heats up, all of that emerges naturally from the statistics of atoms in motion. Think about what he was claiming. He was saying that a law about the macroscopic world, something you can feel with your hand on a warm cup, arises from the collective behavior of things too small to see. That's a staggering intellectual leap, and for a while, it seemed like he'd done it. He'd bridged the gap between the reversible world of Newtonian mechanics and the irreversible world of thermodynamics. But then came the objections, and they were devastating, not because they were wrong, but because they were right. The first major challenge came from a fellow named Joseph Loschmidt, who was actually a friend and colleague of Boltzmann's in Vienna. Loschmidt pointed out something that seems almost too simple to be a real problem, but it cuts right to the heart of the matter. He said, "Look, if the underlying mechanics are time reversible, if every collision between atoms looks the same forward and backward, then how can you possibly derive something irreversible from them? If you take any state of a gas that's evolving toward equilibrium, you could in principle reverse every particle's velocity, and the gas would evolve away from equilibrium, back toward whatever ordered state it started in. The reversed motion obeys exactly the same laws. So how can your H theorem, which says H always decreases, be a genuine consequence of those laws? It can't be a strict mathematical theorem if the laws themselves allow the reverse. This is called the reversibility objection, or sometimes Loschmidt's paradox, and it's one of those arguments that sounds simple, but is actually bottomless. Boltzmann understood it immediately, and to his credit, he didn't dismiss it. he refined his thinking. His response was subtle and, honestly, ahead of its time. He essentially said, "You're right that in principle, the reversed motion is possible. But it's overwhelmingly unlikely. The number of microscopic arrangements that correspond to a disordered, high-entropy state is astronomically larger than the number that correspond to an ordered, low-entropy state. So if you start from any particular state and let the system evolve, it's almost certain to move toward higher entropy simply because there are so many more ways to be disordered than ordered." Here's an analogy that might help. Imagine you have a box divided in half by a partition with all the air molecules on one side and a vacuum on the other. You remove the partition. The gas rushes to fill the whole box. Now, is it physically possible for all the molecules to spontaneously rush back to one side? Yes. The laws of physics allow it. But the probability is so vanishingly small. We're talking 1 divided by a number with more digits than there are atoms in the observable universe, that you would have to wait longer than the age of the universe, many, many times over, for it to happen even once. So in practice, it never happens. Entropy increases not because it must, in some absolute logical sense, but because it's overwhelmingly probable. This was Boltzmann's great insight, and it's the foundation of statistical mechanics as we understand it today. Entropy is not a force. It's not a law in the way that conservation of energy is a law. It's a statistical tendency, an almost certain outcome of the mathematics of large numbers. And that word almost is what makes the whole thing so fascinating and so unsettling, because it means the second law of thermodynamics. This bedrock principle that governs everything from why your body ages to why stars burn out is not a certainty. It's a bet, an extraordinarily good bet, the best bet in all of physics, but still, technically, a bet. Now, Boltzmann thought this settled the matter, but it didn't. A second objection came along, this one from Ernst Zermelo, a young German mathematician who would later become famous for his work in set theory. Zermelo invoked a theorem proved by the French mathematician Henri Poincaré, which says that any mechanical system confined to a finite region of space will, if you wait long enough, return arbitrarily close to its initial state. This is called the Poincaré recurrence theorem. And what Zermelo argued was this: if every state eventually recurs, then any decrease in entropy must eventually be followed by an increase back to the original low entropy state. So the H theorem can't be right, because it predicts a monotonic approach to equilibrium that never reverses, while Poincaré's theorem guarantees that reversals must eventually happen. Boltzmann's response to this was essentially, yes, recurrences will happen, but the timescales involved are so incomprehensibly vast that they have no physical relevance. He reportedly calculated that the recurrence time for even a small container of gas would be something like 10 to the power of 10 to the power of 19 years. That's not just a big number. That's a number so large that writing it down would require more digits than there are particles in the universe. So yes, technically, your cup of coffee will spontaneously reheat itself. You just have to wait an eternity of eternities for it to happen. But here's the thing, and this is where the arrow of time problem really digs its teeth in. Boltzmann's statistical argument explains why entropy increases from any given moment. It explains why, if you find a system in a low entropy state, it will almost certainly evolve toward higher entropy. But it doesn't explain why the universe started in a low entropy state in the first place. And that's the real puzzle. Think about it this way. Boltzmann's reasoning is symmetric. If you pick a random moment in time and ask which direction entropy increases, the statistics say it should increase in both directions. toward the future and toward the past. From any given moment, the most likely history is one where entropy was higher in the past, too. But that's obviously wrong. The universe has a clear record of lower entropy in the past. The cosmic microwave background radiation, the leftover glow from the Big Bang, shows us a universe that was almost perfectly uniform 13.8 billion years ago, a state of extraordinarily low gravitational entropy. Everything since then, the formation of galaxies, stars, planets, you and me, has been a long, slow increase in entropy. The arrow of time points from that low entropy beginning toward the high entropy future. So Boltzmann's statistical mechanics tells us that entropy tends to increase, but it doesn't tell us why there was a low entropy state to increase from. It pushes the question back to the initial conditions of the universe itself. Why did the Big Bang produce such an ordered starting point? This is sometimes called the past hypothesis, a term coined by the philosopher David Albert, and it's essentially the assumption that the universe began in an extremely low entropy state. You have to add this as a separate postulate, on top of the laws of physics, to get the arrow of time to work. The laws alone aren't enough. And that bothered Boltzmann. It bothered him deeply. He actually proposed a remarkable speculation, wild for his time, but eerily resonant with ideas that cosmologists take seriously today. He suggested that maybe the universe as a whole is in thermal equilibrium, a vast, featureless sea of maximum entropy, and that what we observe around us is just a local fluctuation, a random dip in entropy that happened by chance and is slowly returning to equilibrium. We happen to exist during this fluctuation, he argued, because the conditions for life require low entropy. It's a kind of proto-anthropic reasoning, decades before anyone used that term. The problem with this idea, as later physicists realized, is that it leads to strange conclusions. If you're just a random fluctuation, then the most likely fluctuation that produces an observer like you is the smallest possible one, just a brain floating in the void with false memories of a universe that doesn't actually exist. These hypothetical entities are now called Boltzmann brains, and the fact that they seem to be predicted by certain cosmological models is considered a serious problem, a sign that something has gone wrong with your assumptions. But Boltzmann never lived to see these debates play out. His story has a tragic ending. Throughout the 1890s, the attacks on his work intensified. The philosopher-physicist Ernst Mach, enormously influential in Vienna, openly rejected the reality of atoms and dismissed Boltzmann's statistical approach as metaphysical speculation. Wilhelm Ostwald, a leading chemist, championed an alternative framework called energetics that tried to do away with atoms entirely. Boltzmann found himself increasingly isolated, defending ideas that he believed were correct, but that the scientific establishment of his time refused to accept. He suffered from severe depression, possibly bipolar disorder. His health deteriorated, and in September 1906, while on vacation with his family in Duino, near Trieste, Ludwig Boltzmann took his own life. He was 62 years old. The cruel irony is that vindication was already on its way. Just the year before, in 1905, a young patent clerk in Bern named Albert Einstein had published a paper on Brownian motion, the random jiggling of tiny particles suspended in liquid, that provided strong evidence for the physical reality of atoms. A few years later, Jean Perrin's meticulous experiments confirmed Einstein's predictions and essentially settled the debate. Atoms were real. Boltzmann had been right all along. On his tombstone in Vienna, they engraved his entropy formula, S equals K log W. It's one of the most beautiful equations in all of physics, and it says that the entropy of a system is proportional to the logarithm of the number of microscopic arrangements compatible with its macroscopic state. That single equation connects the world you can see and touch to the world of atoms you can't, and it does so through the mathematics of probability. But even with Boltzmann vindicated, the arrow of time problem didn't go away. If anything, it got deeper. Because in the 20th century, physics discovered new laws, new symmetries, and new reasons to be puzzled. And one of the most unexpected twists came not from thermodynamics at all, but from the quantum world, from the strange behavior of subatomic particles that seemed to follow rules that nobody had written down, rules that didn't seem to care about the direction of time in the way you'd expect, and yet somehow, when you looked closely enough, contained a tiny, almost imperceptible crack in the symmetry, a crack that might, just might, have something to do with why the past is different from the future. So let's talk about quantum mechanics. And I want to approach this gently, because quantum mechanics has a reputation for being impossibly weird, and it is weird, but the core ideas are actually graspable if you come at them the right way. The strangeness isn't in the math. The math is precise and beautiful. The strangeness is in what the math seems to be telling us about reality, and that's where the unsolved questions live. Here's where it starts. In the early 1900s, right around the time Boltzmann was fighting his lonely battle about atoms, physicists were running into problems with light. Specifically, they were trying to understand how light interacts with matter at the smallest scales, and the classical theories, Maxwell's elegant equations of electromagnetism, kept giving wrong answers. Remember Lord Kelvin's two clouds? One of them was the ultraviolet catastrophe, the prediction that a hot object should radiate infinite energy at short wavelengths. Classical physics said that if you heated up, say, an oven, the energy should pile up more and more at higher and higher frequencies, ultraviolet, then X-rays, then beyond, without limit. Obviously, that doesn't happen. Your oven glows red, then white, but it doesn't blast you with gamma rays. Something was wrong with the theory. In 1900, Max Planck found a fix, but it was a fix he didn't entirely like. He proposed that energy isn't emitted continuously, the way water flows from a tap, but in discrete packets, quanta. Each quantum of energy is proportional to the frequency of the radiation, with the proportionality constant being a tiny number now called Planck's constant, usually written as h. It's incredibly small, about 6.6 times 10 to the negative 34 joule-seconds. That smallness is why you don't notice quantization in everyday life. The packets are so tiny that energy looks smooth at human scales, the same way a beach looks smooth from an airplane even though it's made of individual grains of sand. Planck himself thought this was probably just a mathematical trick, a clever bookkeeping device that happened to give the right answer. He didn't really believe energy was fundamentally granular. But then Einstein, the same Einstein who vindicated Boltzmann's atoms, took the idea seriously. In 1905, that miraculous year when he published not one but 4 groundbreaking papers, one of them argued that light itself comes in quanta, particles of light that we now call photons. He used this to explain the photoelectric effect, the observation that shining light on a metal surface can knock electrons loose, but only if the light's frequency is high enough. Classical wave theory couldn't explain why frequency mattered. If light were just a wave, you should be able to knock electrons loose with any frequency, as long as you used enough intensity, like pushing someone on a swing harder and harder. But that's not what happens. Below a certain frequency, nothing happens no matter how bright the light. Einstein's explanation was simple and radical. Each photon carries a specific amount of energy determined by its frequency. And if that energy isn't enough to liberate an electron, then it doesn't matter how many photons you throw at the surface. None of them individually have enough punch. This was wild. Light, which everyone knew was a wave, interference patterns, diffraction, all the beautiful experiments that proved it, was also, somehow, a particle. Not one or the other. Both, depending on how you looked at it. And then it got stranger. In 1924, a French physicist named Louis de Broglie, working on his doctoral thesis, proposed that this duality went both ways. If waves could behave like particles, then particles could behave like waves. Electrons, protons, atoms, all of them should have a wavelength associated with their motion. And within a few years, experiments confirmed it. You could shoot electrons through a crystal and see them produce interference patterns, the same kind of patterns you get when water waves pass through two openings. Electrons, tiny bits of matter with definite mass and charge, were interfering with themselves like waves on a pond. Now think about what that means for a second. If you send a single electron toward a barrier with two slits in it, and you put a detector screen on the other side, and you do this over and over, one electron at a time, you'd expect each electron to go through one slit or the other and build up two bands on the screen. That's what particles should do. But that's not what happens. Instead, you get an interference pattern alternating bright and dark bands, as if each electron somehow went through both slits simultaneously and interfered with itself. One electron, both slits. An interference pattern that only makes sense if you treat the electron as a wave that passes through both openings at once. But here's the really strange part, and this is the part that still keeps physicists up at night. If you put a detector at the slits to watch which slit the electron actually goes through, the interference pattern disappears. You get the two simple bands you'd expect from particles. The act of observing which path the electron takes seems to change the outcome. It's as if the electron knows it's being watched. This is the measurement problem, and it is, I think, the deepest unsolved question in all of physics. It's not just a puzzle about electrons and slits. It goes to the heart of what quantum mechanics is actually telling us about reality. Here's the thing. Quantum mechanics gives us an extraordinarily precise mathematical framework for predicting the outcomes of experiments. At its core is the wave function, usually written with the Greek letter psi. The wave function describes the state of a quantum system, an electron, a photon, an atom, and it evolves over time according to a beautiful, deterministic equation called the Schrödinger equation, named after the Austrian physicist Erwin Schrödinger, who wrote it down in 1926. Deterministic is the key word here. If you know the wave function at one moment, the Schrödinger equation tells you exactly what it will be at any future moment. No randomness, no ambiguity. It's as clockwork as Newton's laws. But, and this is the big but, the wave function doesn't directly tell you what you'll observe. What it gives you are probabilities. The square of the wave function at a given point tells you the probability of finding the particle there if you look. Before you look, the particle doesn't have a definite position. It's not that you don't know where it is. According to the standard interpretation of quantum mechanics, it genuinely doesn't have a definite position. It exists in what's called a superposition. a combination of many possible positions all at once, each with a certain probability amplitude. And then you measure it, and something happens. The wave function, which was spread out over many possibilities, suddenly collapses to a single definite outcome. The electron is here, not there. The photon went through this slit, not that one. This collapse is instantaneous, random, and irreversible. And here's what's so troubling about it. The collapse doesn't follow the Schrödinger equation. It's a completely different kind of process. The Schrödinger equation is smooth, continuous, deterministic. Collapse is sudden, discontinuous, probabilistic. Quantum mechanics seems to have two completely different rules, one for when you're not looking and one for when you are. This bothered a lot of people from the very beginning. Einstein hated it. He famously said that God does not play dice, expressing his conviction that the randomness of quantum mechanics must be a sign that the theory was incomplete, that there were hidden variables underneath that, if you could find them, would restore determinism. He and two colleagues, Boris Podolsky and Nathan Rosen, wrote a paper in 1935 arguing that quantum mechanics couldn't be a complete description of reality. Their argument involved what we now call entanglement, the strange quantum connection between particles that have interacted and then separated. Two entangled particles can be miles apart, and yet measuring one instantly seems to affect the other. Einstein called this spooky action at a distance, and he meant it as a criticism. Niels Bohr, the great Danish physicist who was the intellectual architect of the standard interpretation, pushed back. He argued that you couldn't talk about what a particle is doing before you measure it. The measurement isn't revealing a pre-existing reality. It's participating in creating the reality. The question, which slit did the electron go through, doesn't have an answer until you set up an experiment to answer it. Bohr's view, which became known as the Copenhagen interpretation, essentially said, stop asking what's really happening between measurements. The theory gives you predictions for measurement outcomes. That's all physics can do. That's all physics should do. And for decades, most physicists accepted this. Not because it was satisfying, it wasn't, but because it worked. Quantum mechanics, with its strange rules about superposition and collapse, made predictions that were confirmed to extraordinary precision. The magnetic moment of the electron, for instance, has been calculated using quantum electrodynamics and measured experimentally, and the two agree to better than 10 parts in a billion. It's the most precisely confirmed prediction in the history of science. So, whatever quantum mechanics is doing, it's doing it right. But the measurement problem didn't go away, and people kept poking at it, kept asking the uncomfortable questions that Bohr had tried to declare off limits. One of the most vivid ways to see the problem is through a thought experiment that Schrödinger himself proposed in 1935, partly as a way of showing how absurd the standard interpretation was when you pushed it to its logical conclusion. You've probably heard of it. You put a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, a quantum event with, say, a 50-50 chance of happening within an hour, the Geiger counter triggers, the vial breaks, and the cat dies. If the atom doesn't decay, the cat lives. According to quantum mechanics, before you open the box, the atom is in a superposition of decayed and not decayed. And if the atom is in a superposition, then the Geiger counter is in a superposition of triggered and not triggered, and the vial is in a superposition of broken and intact, and the cat is in a superposition of alive and dead. The cat is both alive and dead at the same time until you open the box and look. Now, Nobody actually believes the cat is both alive and dead. That's the point. Schrödinger was highlighting the absurdity of applying quantum superposition to everyday objects. But the question is, where does the quantum world end and the classical world begin? At what point does the superposition collapse into a definite outcome? Is it when the Geiger counter clicks? When the poison is released? When the cat's neurons fire? When you open the box? When the information reaches your consciousness? There's no clear answer, and that's the measurement problem in a nutshell. Several competing interpretations have been proposed, and here's what's fascinating. They all agree on the predictions. They all give you the same experimental outcomes. They disagree about what's actually happening underneath. The Copenhagen interpretation says, don't ask. The many worlds interpretation, proposed by Hugh Everett in 1957, says the wave function never collapses at all. Instead, every possible outcome actually happens, but in separate branches of a constantly splitting universe. When you open the box, you don't find the cat alive or dead. You split into two versions of yourself, one who sees a live cat and one who sees a dead cat. And both versions are equally real, existing in separate branches of an unimaginably vast multiverse. The pilot wave theory, developed by Louis de Broglie and later refined by David Bohm, says particles do have definite positions at all times, guided by a real wave, and the apparent randomness comes from our ignorance of the initial conditions. There are others, objective collapse theories, that modify the Schrödinger equation to include a physical collapse mechanism, relational interpretations, information theoretic approaches. And here's the kicker. We don't know which one is right. As of right now, in the 21st century, after more than 100 years of quantum mechanics, we do not have a consensus on what the theory is actually telling us about the nature of reality. We have a mathematical machine that generates predictions with breathtaking accuracy, and we do not agree on what it means. Now, you might be thinking, does it matter? If all the interpretations give the same predictions, isn't the question purely philosophical? And some physicists would say yes, it's philosophy, not physics, and we should just shut up and calculate. That phrase, shut up and calculate, is often attributed to Richard Feynman, though he may never have actually said it quite that way. But here's why I think it matters, and why a lot of physicists think it matters. Because the measurement problem isn't just about interpretation. It's connected to the deepest, unsolved problems in physics. It's connected to the arrow of time, because wave function collapse is irreversible, introducing a time asymmetry into a theory whose fundamental equation is time symmetric. It's connected to quantum gravity, because we don't know how to apply quantum mechanics to the entire universe when there's no external observer to make measurements. And it's connected to the nature of information, because information might be the most fundamental thing there is. More fundamental than matter, more fundamental than energy, more fundamental even than space and time themselves. And that idea, that information sits at the bottom of everything, is one of the strangest and most compelling threads in modern physics. So let's pull on it. Start with a simple question. What is information? In everyday life, you think of information as facts, data, stuff written in books or stored on hard drives. But in physics, information has a much more precise meaning, and it goes back to a guy named Claude Shannon. Shannon was an electrical engineer at Bell Labs, and in 1948, he published a paper called A Mathematical Theory of Communication that essentially invented the field of information theory. What Shannon realized was that information could be quantified, measured in bits, binary digits, ones and zeros, and that the amount of information in a message was related to how surprising it was. If I tell you the sun rose this morning, that's not very informative, because you already expected it. But if I tell you it didn't rise, that's extremely informative, because it's unexpected. Shannon formalized this intuition mathematically, and in doing so, he noticed something remarkable. The equation he derived for information entropy, the measure of uncertainty or surprise in a system, looked almost identical to the equation Boltzmann had written down for thermodynamic entropy decades earlier. The resemblance was so striking that John von Neumann reportedly told Shannon to go ahead and call it entropy, partly because nobody really understands entropy, so in a debate, Shannon would always have the advantage. That's a great joke, but it also hints at something deep. Is the similarity between information entropy and thermodynamic entropy just a mathematical coincidence, or does it point to a real physical connection? And the answer, as far as we can tell, is that it's real. Information and thermodynamic entropy are not just analogous. They are, in some fundamental sense, the same thing. Here's one way to see it. Remember Maxwell's demon? James Clerk. Maxwell proposed this thought experiment back in 1867. Imagine a box of gas divided into two halves by a wall with a tiny door. A little demon sits at the door, watching the gas molecules. When a fast molecule approaches from the left, the demon opens the door and lets it through to the right. When a slow molecule approaches from the right, the demon lets it through to the left. Over time, the fast molecules accumulate on one side and the slow ones on the other. One side gets hot, the other gets cold. The demon has decreased the entropy of the gas without doing any work, apparently violating the second law of thermodynamics. For over a century, this was a genuine puzzle. People proposed various solutions. Leo Szilard, in 1929, argued that the demon's act of measurement, gaining information about each molecule's speed, must itself generate entropy, balancing the books. But the full resolution didn't come until 1961, when Rolf Landauer, another researcher at IBM, proved something astonishing. Landauer showed that erasing information, not acquiring it, but erasing it, has a minimum thermodynamic cost. Every time you erase one bit of information, you must dissipate at least a tiny amount of energy as heat, increasing the entropy of the environment. This is Landauer's principle, and it's been experimentally verified. Think about what that means. The demon has to store information about each molecule in its memory. Eventually, its memory fills up, and it has to erase old information to make room for new measurements. That erasure generates heat, which increases entropy. And when you do the full accounting, the second law is preserved. The demon can't win. But the reason it can't win is profoundly revealing. It tells us that information is physical. It's not abstract. It's not just something in our heads. Information is inscribed in the physical state of a system, and manipulating it has real physical consequences. Erasing a bit costs energy. Storing a bit requires a physical medium. Information obeys the laws of thermodynamics. Now, this connection between information and physics might seem like a curiosity, a neat little resolution to a thought experiment, but it turns out to be far more consequential than that, because it leads directly to one of the deepest unsolved problems in all of physics, the black hole information paradox. And to understand that, we need to talk about black holes. You've heard of them, of course. A black hole is a region of space-time where gravity is so intense that nothing, not even light, can escape once it crosses a boundary called the event horizon. The idea goes back surprisingly far. Jean Michel speculated about dark stars in 1783, and Pierre-Simon Laplace independently had a similar idea. But the modern understanding comes from general relativity. In 1915, just weeks after Einstein published his field equations, a German physicist named Karl Schwarzschild, who was serving on the Eastern Front in World War I of all things, found an exact solution describing the spacetime around a perfectly spherical, non-rotating mass. His solution contained a mathematical singularity at a particular radius, what we now call the Schwarzschild radius. For decades, most physicists, including Einstein himself, thought black holes were just mathematical curiosities that wouldn't actually form in nature. It wasn't until the 1960s, through the work of Roger Penrose, John Wheeler, who actually coined the term black hole in 1967, and others, that the physics community accepted that black holes were real predictions of general relativity, and that they could and probably did form when massive stars collapsed at the end of their lives. Here's the thing about black holes from a classical general relativity perspective. They're remarkably simple. A black hole is completely described by just three properties: its mass, its electric charge, and its angular momentum, how fast it's spinning. That's it. This is called the no-hair theorem, and Wheeler summarized it beautifully. Black holes have no hair. What he meant is that no matter what you throw into a black hole, a book, a piano, a star, a collection of love letters, the black hole retains no memory of what went in. It only remembers the total mass, charge, and spin. All the detailed information about the stuff that fell in appears to be gone, erased, lost. And if that were the end of the story, it would already be uncomfortable, because it seems to violate something physicists hold very dear: the principle that information is never truly destroyed. In quantum mechanics, the evolution of a system is described by the Schrödinger equation, which is unitary. Unitarity means, roughly, that the equation is reversible. If you know the final state of a system, you can in principle work backward and figure out the initial state. Information is preserved. It might get scrambled, rearranged, spread out in ways that make it practically impossible to recover, but it's always there in principle. It's never gone. The laws of physics, at their most fundamental level, don't allow information to vanish. So you already have attention. Classical general relativity says information falls into a black hole and disappears. Quantum mechanics says information can never be destroyed. But the real crisis didn't arrive until 1974, when Stephen Hawking dropped a bombshell. Hawking had been thinking about what happens when you apply quantum mechanics to the region near a black hole's event horizon, and he discovered something nobody expected. Black holes aren't completely black. They emit radiation, a faint, steady glow of particles, and this radiation causes the black hole to slowly lose mass and shrink. Given enough time, the black hole evaporates entirely. It's gone. This is Hawking radiation, and it's one of the most important theoretical discoveries of the 20th century, because it was the first concrete result combining quantum mechanics and gravity. But here's what's wild about Hawking radiation. The radiation is thermal. It's random. It carries no information about what fell into the black hole. It's like the heat radiating from a warm object. It tells you the temperature, but nothing about the object's internal structure. So if a black hole forms, swallows a library's worth of information, and then evaporates completely into featureless thermal radiation, where did the information go? It seems to have been destroyed. Genuinely, irreversibly destroyed. And that contradicts the unitarity of quantum mechanics. This is the black hole information paradox, and it has consumed theoretical physics for 50 years. Hawking himself initially argued that information was indeed lost, that black holes represented a fundamental breakdown of quantum mechanics. He made a famous bet with Caltech physicist John Preskill in 1997. Hawking wagered that information was destroyed. Preskill bet it was preserved. And in 2004, Hawking conceded the bet, saying he'd come to believe information was preserved after all, though his proposed mechanism wasn't entirely convincing to everyone. He gave Preskill a baseball encyclopedia. The information, he joked, was preserved. But the concession didn't resolve the paradox, because we still don't have a complete, satisfying explanation of how the information gets out. There are proposals. One of the most influential came from Juan Maldacena in 1997, the same year as the bet, actually, when he proposed the ADS/CFT correspondence, a mathematical duality between a theory of gravity in a certain kind of spacetime and a quantum field theory without gravity living on the boundary of that spacetime. In the boundary theory, everything is manifestly unitary. Information is preserved by construction. So if the duality is correct, information must also be preserved in the gravitational theory, even when black holes form and evaporate. This was enormously influential and convinced many string theorists that information is indeed preserved. But it doesn't tell you the mechanism. It doesn't explain how the information escapes. More recently, in 2019 and 2020, a series of remarkable papers by Ahmed Almheri, Netta Engelhardt, Donald Marolf, Henry Maxfield, Jeff Pennington, and others made dramatic progress using a concept called the island formula, which modifies how we calculate the entropy of Hawking radiation. Their calculations suggest that the entropy of the radiation follows what's called the Page curve, named after Don Page, who argued back in 1993 that if information is preserved, the entropy of the radiation should rise and then fall in a specific way as the black hole evaporates. The new calculations reproduce this curve, strongly suggesting information does get out. But even these results raise as many questions as they answer. They rely on mathematical tools whose physical interpretation is still debated. They work beautifully in certain simplified models, but haven't been fully extended to realistic black holes in our universe. And they hint at something deeply strange about the nature of space-time itself, that the geometry of space inside a black hole might be connected to the entanglement structure of the radiation outside it in ways we don't fully understand. And this is where the information paradox connects to something even bigger, because the attempts to resolve it keep pointing toward a radical idea that space-time itself might not be fundamental. That space, the three-dimensional arena we move through every day, and time, the dimension we seem to flow along, these might be emergent. They might arise from something deeper, and that something deeper might be entanglement, quantum entanglement. There's a beautiful conjecture by Maldacena and Leonard Susskind from 2013, often abbreviated ER equals EPR. ER refers to Einstein-Rosen bridges, wormholes, which are solutions to general relativity connecting distant regions of spacetime. EPR refers to Einstein-Podolsky-Rosen entanglement, the quantum correlations between distant particles. The conjecture says these are the same thing, that every pair of entangled particles is connected by a tiny wormhole, that the fabric of spacetime is literally stitched together by quantum entanglement, and if you removed all the entanglement, space itself would fall apart, like a garment with every thread pulled out. If that's true, and it's still a conjecture, still unproven, then the question of what space-time is made of, The question of how gravity and quantum mechanics fit together, and the question of what happens to information in a black hole are all the same question, seen from different angles. And we don't have the answer yet. We have tantalizing hints, brilliant partial results, mathematical frameworks that work in toy models, but the full picture remains incomplete. Like a jigsaw puzzle where you've assembled enough pieces to see the outline of the picture, maybe even some of the central figures, but whole sections are still missing and you're not even sure all the pieces are in the box. So let's sit with that for a moment. Because the puzzle we're circling, how gravity and quantum mechanics fit together, is arguably the deepest open question in all of physics. And to really appreciate why it's so hard, and why so many brilliant people have spent decades on it without a definitive answer, we need to understand what each theory actually says about the world, and why those two descriptions seem to fundamentally contradict each other. Think about general relativity first. Einstein's masterpiece. It tells you that space-time is a smooth, continuous fabric, a manifold in the mathematical language, and that matter and energy curve that fabric, and that curvature is what we experience as gravity. It's a gorgeous geometric picture. The equations are deterministic. You tell me the distribution of matter and energy, and I can calculate exactly how space-time curves, how objects move, what happens next. There's no randomness, no probability, just geometry. Now think about quantum mechanics. It tells you that at the smallest scales, everything is described by wave functions, by probability amplitudes. Particles don't have definite positions until they're measured. Energy comes in discrete chunks. The vacuum itself seethes with fluctuations, pairs of particles popping in and out of existence on timescales so short that the uncertainty principle allows it. And crucially, the stage on which quantum mechanics performs, the background against which all these quantum events happen, is a fixed, predetermined space-time. Quantum mechanics takes the geometry of space and time as given, as a stage that's already set, and then describes how quantum fields dance on that stage. You see the problem, right? General relativity says space-time is dynamic. It bends, it warps, it responds to what's in it. Quantum mechanics says space-time is a fixed background. It's the stage, not a performer. General relativity is smooth and continuous. Quantum mechanics is grainy and probabilistic. Each theory works spectacularly well in its own domain. General relativity describes the large-scale structure of the universe, galaxies, black holes, the expansion of the cosmos. Quantum mechanics describes the small-scale structure, atoms, particles, forces. But when you need both at the same time, when you have something that's both very massive and very small, the two theories don't just disagree. They produce nonsense, infinities, contradictions, answers that can't possibly be right. And there are real physical situations where you need both. The singularity at the center of a black hole, where all the mass is compressed to a point of infinite density. The first instant of the Big Bang, when the entire observable universe was smaller than an atom, but contained all the mass and energy we see today. These aren't exotic thought experiments. These are things that actually happened, or are happening right now, in black holes scattered across the cosmos. And we cannot describe them. Our best theories literally break down. This is the problem of quantum gravity. And people have been working on it, seriously and intensely, since at least the 1930s. That's almost a century. And we still don't have a complete, experimentally verified theory, which should tell you something about how hard this is. The most straightforward approach, the thing you'd try first if you were being naive about it, is to just quantize gravity the same way we quantized electromagnetism. Take the gravitational field, apply the standard quantum mechanical rules, and see what happens. With electromagnetism, this worked beautifully. You get quantum electrodynamics, QED, which Richard Feynman and Julian Schwinger and Shinichiro Tominaga developed in the late 1940s. It's the most precisely tested theory in all of science. Its predictions match experiments to something like 10 decimal places. Stunning. So you try the same thing with gravity. You write down the gravitational field, you try to quantize it, and you get a particle, the graviton, the hypothetical quantum of the gravitational field, just as the photon is the quantum of the electromagnetic field. And at first, things seem okay. You can calculate simple processes, but then you try to calculate more complicated ones, higher order corrections, the kind of thing that's routine in QED, and you get infinities, and not the kind of infinities you can tame. Here's the thing about QED. It also produces infinities in its calculations. But Feynman and the others figured out a procedure called renormalization, a systematic way to absorb those infinities into the definitions of physical quantities like mass and charge. It sounds like a trick, and Feynman himself called it sweeping the infinities under the rug. But it works. It gives you finite, meaningful, testable predictions. And the reason it works is that QED only has a finite number of types of infinities. You can catalog them all and deal with each one. Gravity is different. When you try to quantize it the same way, you get an infinite number of types of infinities. Every time you go to a higher order of calculation, new kinds of divergences appear, and you'd need an infinite number of new parameters to absorb them all, which means the theory has no predictive power. It can't tell you anything because you'd need to measure infinitely many constants from experiment before you could predict anything else. Physicists call this non-renormalizable, and it's not just a technical inconvenience. It's a sign that something fundamental is wrong with the approach, that gravity doesn't want to be quantized the same way as the other forces. This was understood pretty clearly by the 1970s and 1980s, and it sent people in two very different directions. Two big research programs that have dominated theoretical physics for decades, each with passionate advocates, each with remarkable achievements, and each with serious unresolved problems. The first is string theory, and you've probably heard the name, even if you're not sure what it actually says. The basic idea, which emerged in the late 1960s and early 1970s from some work on the strong nuclear force that turned out to be wrong for that purpose but right for something else, is this. What if the fundamental constituents of nature aren't point particles? What if they're tiny, one-dimensional vibrating strings, unimaginably small, on the order of the Planck length, about 10 to the minus 35 meters? A string can vibrate in different modes, different patterns, just like a guitar string can produce different notes. And each mode of vibration corresponds to a different particle. One mode gives you a photon, another gives you an electron. And here's what got people really excited. One mode naturally gives you a graviton, a massless spin-2 particle, which is exactly what you need for quantum gravity. String theory doesn't just accommodate gravity, it demands it. Gravity falls out of the mathematics whether you want it or not. And when you calculate gravitational interactions in string theory, the infinities that plagued the naive approach don't appear. The extended nature of the string smears things out at very short distances, acting like a natural regulator. It's as if the string can't probe distances shorter than its own length. And that's exactly where the infinities in the old approach were coming from. This was genuinely thrilling when people realized it in the mid-1980s. There was a period, sometimes called the first superstring revolution, when it seemed like string theory might be the answer. Michael Green and John Schwartz showed in 1984 that certain potential inconsistencies in the theory, called anomalies, canceled out in a specific version of string theory. The news spread through the physics community like wildfire. Ed Witten, widely regarded as one of the greatest mathematical physicists alive, threw his weight behind it. Within months, hundreds of physicists pivoted their research programs to work on strings. But then the complications set in. String theory requires extra dimensions of space, not 3, but 9 spatial dimensions, or 10 if you include time. The extra 6 dimensions are supposed to be curled up so small we can't see them, compactified into tiny geometric shapes called Calabi-Yau manifolds. And the specific shape of those extra dimensions determines the physics we observe, which particles exist, what their masses are, how they interact. The problem is that there are an enormous number of possible shapes. Not just a few, not hundreds, not thousands. Current estimates suggest something like 10 to the 500 possible configurations. That's a number so large it's essentially meaningless, far more than the number of atoms in the observable universe. This is the landscape problem. String theory doesn't predict one unique universe. It predicts a vast landscape of possible universes, each with different physics. And we don't have a mechanism to select which one is ours. Some people see this as a fatal flaw. A theory that can predict anything predicts nothing. Others see it as a feature, arguing that perhaps all these universes exist in some multiverse, and we happen to live in one compatible with our existence. This is the anthropic approach, and it's deeply controversial. It feels, to many physicists, like giving up on the traditional goal of physics, which is to explain why the universe is the way it is. And there's another problem, one that cuts even deeper. String theory, as of today, has made no experimentally testable predictions that differ from existing theories. None. The energy scales at which stringy effects would become visible are so far beyond what any conceivable particle accelerator could reach that direct experimental tests seem impossible. This doesn't mean the theory is wrong. But it does mean we can't confirm it's right. And for a scientific theory, that's a deeply uncomfortable position. The second major approach is loop quantum gravity, and it takes a completely different philosophical starting point, where string theory adds new ingredients, strings, extra dimensions, supersymmetry. Loop quantum gravity tries to quantize gravity directly, using only the ingredients Einstein gave us, but with a radically different mathematical framework. It was pioneered in the mid-1980s by Abhay Ashtekar, who found a way to reformulate general relativity using new variables that made it look more like the gauge theories that describe the other forces. Then Lee Smolin and Carlo Rovelli, building on Ashtekar's work in the early 1990s, showed that when you quantize this reformulation, something remarkable happens. Space itself becomes discrete. It's not smooth and continuous at the smallest scales. It's made of finite chunks, quanta of geometry. The theory predicts a minimum possible volume, a minimum possible area. Space has a granular structure at the Planck scale, like a fabric that looks smooth from a distance but is actually woven from discrete threads. These threads form structures called spin networks, graphs, where the edges carry quantum numbers related to area and volume, and the evolution of spin networks over time gives you spin foams, which are supposed to be the quantum version of spacetime itself. It's a beautiful mathematical picture. And unlike string theory, it doesn't require extra dimensions. It works in the 4 dimensions we actually observe. But loop quantum gravity has its own deep problems. The biggest one is that no one has convincingly shown that it reproduces general relativity in the appropriate limit. If you zoom out from the Planck scale, if you look at the large-scale behavior of these spin networks, you should recover Einstein's smooth spacetime and his equations of gravity. And while there's been progress on this, it hasn't been definitively demonstrated. There's also the question of matter. Loop quantum gravity is primarily a theory of quantum spacetime geometry. Incorporating the other forces and particles, the stuff described by the Standard Model, has proven difficult. String theory naturally includes matter. Loop quantum gravity has to add it in by hand, and it's not always clear how. So here we are. 2 major approaches to quantum gravity, both decades old, both mathematically rich, both with devoted communities of researchers, and neither one complete, neither one experimentally confirmed. And this is where things stand as of right now, which is both humbling and, in a strange way, exciting, because it means the answer is still out there. The deepest question about the nature of space and time remains genuinely open. And lately, there's been a fascinating convergence. Ideas from string theory, and ideas from loop quantum gravity, and ideas from quantum information theory have started to overlap in unexpected ways. That ER equals EPR conjecture we talked about. The idea that entanglement and wormholes are the same thing. That came from the string theory side, but its implications reach far beyond any one framework. And the notion that space-time emerges from entanglement, that geometry is somehow built from quantum information, has attracted people from all camps. There's a concept that's been gaining traction, something called the holographic principle, and it connects to almost everything we've been discussing. It started with an observation by Jacob Bekenstein in the early 1970s, the same work that led to black hole thermodynamics. Bekenstein showed that the maximum entropy, the maximum amount of information that can be contained in a region of space, is not proportional to the volume of that region, as you might naively expect, but to the area of its boundary. Think about that. If you have a room, the total information content of everything inside that room is limited not by how big the room is, but by how big the walls are. It's as if the 3-dimensional interior is somehow encoded on the 2-dimensional surface, like a hologram, where a flat piece of film contains all the information needed to reconstruct a 3-dimensional image. Gerard T. Hooft formalized this into a principle in 1993, and Susskind developed it further, and then Maldaceno's ADS/CFT correspondence in 1997 provided the first concrete mathematical realization. A theory of gravity in a volume of space-time is exactly equivalent to a quantum theory without gravity living on the boundary of that space-time. The bulk and the boundary contain the same information, described in completely different languages. And this isn't just a metaphor or an analogy. It's a precise mathematical duality. You can translate calculations from one side to the other and get the same answers. Now, what does this mean for the nature of reality? If the holographic principle is correct, and there's substantial evidence that it is, at least in certain contexts, then one of the dimensions of space is, in some sense, redundant. It's emergent. It can be reconstructed from information encoded in a lower dimensional theory. And if one dimension can be emergent, why not all of them? Why not time itself? Why not the whole fabric of space-time, every direction, every tick of the clock? What if space and time aren't the stage on which physics happens, but are themselves the performance. Something that emerges from a deeper layer of reality that has no space and no time at all. That idea sounds almost mystical when you say it out loud. It sounds like the kind of thing someone might say at the end of a long night when the conversation has drifted into philosophy and everyone's a little too tired to push back. But here's the thing. This isn't philosophy. Or at least, it's not only philosophy. Some of the most serious, technically rigorous work in theoretical physics right now is built on exactly this premise. And the trail of evidence, circumstantial as it may be, keeps growing. Let's stay with the holographic principle for another moment, because there's a specific result that really drives the point home. In 2006, a physicist named Shinsei Ryu and a collaborator, Tadashi Takayanagi, proposed a beautifully simple formula. They were working within the ADS/CFT framework. That duality Maldacena discovered, where a gravitational theory in a curved spacetime is equivalent to a quantum theory on its boundary. Ryu and Takayanagi asked a natural question. If you have a region on the boundary theory, and you want to know how entangled that region is with the rest of the boundary, how do you calculate that entanglement entropy? And their answer was stunning. You calculate it by finding the minimal surface in the bulk, the smallest area surface that hangs down into the higher dimensional spacetime and is anchored to the edge of your boundary region. The entanglement entropy equals the area of that surface, divided by 4 times Newton's gravitational constant. The same formula as Bekenstein-Hawking entropy for black holes, but now generalized. Think about what that's saying. The geometry of the interior spacetime, the shape of the bulk, the way distances work, how curves bend, all of that is being determined by patterns of entanglement in the boundary theory. Entanglement, which is a purely quantum phenomenon, a correlation between quantum states, is somehow stitching together the geometry of space. More entanglement between 2 boundary regions means those regions are closer together in the bulk. Less entanglement means they're farther apart. If you remove the entanglement entirely, the spacetime literally tears. It disconnects. Mark van Ramsdonk, a physicist at the University of British Columbia, wrote a wonderful paper around 2010 making this argument very explicitly. He showed that if you start with a state in the boundary theory that has lots of entanglement and you gradually reduce it, the corresponding bulk spacetime develops a longer and longer bottleneck, like a bridge being stretched thinner and thinner, until it pinches off completely when the entanglement reaches 0. Space, in this picture, is literally held together by quantum entanglement. That's not a metaphor. That's what the mathematics says. And this connects back to that ER equals EPR conjecture we talked about earlier, the one from Maldacena and Susskind. Einstein-Rosen bridges, wormholes, are the same thing as Einstein-Podolsky-Rosen correlations, entanglement. Every pair of entangled particles is connected by a tiny, Planck-scale wormhole. The geometry of spacetime is woven from threads of entanglement. It's a breathtaking idea. And while it hasn't been proven in full generality, every calculation that's been done within the frameworks where we can calculate seems to support it. So, now we're in genuinely strange territory. We started this whole journey talking about the questions physics can't answer, and here we are at a place where the question isn't about some exotic phenomenon at the edge of a black hole or the first fraction of a second after the Big Bang. The question is about the nature of space and time themselves. Are they fundamental? Are they part of the basic furniture of reality? Or are they emergent, approximate, large-scale descriptions that arise from something deeper, the way temperature arises from the motion of molecules, the way the smooth surface of water arises from the chaos of trillions of individual molecules bouncing around. If space-time is emergent, then what's the underlying thing? What are the atoms of space-time? The way water molecules are the atoms of a fluid. This is one of the deepest open questions in all of physics, and the honest answer is, we don't know. But there are clues, and they keep pointing in the same direction. One clue comes from a research program called It from Qubit. The name is a play on John Wheeler's famous phrase, "it from bit," the idea that information is the foundation of physical reality. Wheeler coined that phrase back in the late 1980s, and at the time, it was more of a philosophical stance than a research program. But in the last decade or so, a community of physicists working at the intersection of quantum information theory and quantum gravity has turned it into something much more concrete. The qubit version emphasizes that it's specifically quantum information. Qubits, entanglement, quantum error correction, that seems to underlie the structure of space-time. And here's where it gets really interesting. Around 2014 and 2015, a group of researchers including Ahmed Almheiri, Shi Dong, and Daniel Harlow showed that the way the holographic correspondence works, the way information in the bulk space-time is encoded in the boundary theory, has exactly the structure of a quantum error correcting code. Now, quantum error correction is something that was developed for a completely practical reason. If you want to build a quantum computer, you need to protect your delicate quantum information from noise and errors. You do this by encoding the information redundantly, spreading it across many qubits in a clever way, so that even if some qubits get corrupted, you can still recover the original information. What Almheiri, Dong, and Harlow showed is that the holographic dictionary, the map between bulk and boundary, works in precisely this way. A piece of information located at a point deep in the bulk space-time is encoded redundantly across many degrees of freedom on the boundary. You can lose access to part of the boundary and still reconstruct what's happening in the bulk, just like you can lose some qubits in an error-correcting code and still recover your data. That's remarkable. It means the universe might be structured like a quantum computer's error-correcting code, not metaphorically, structurally. The mathematics is the same. And this gives us a new way to think about why space-time has the properties it does. The smoothness of space, the fact that nearby points have similar properties, the way geometry bends in response to energy. All of these might be consequences of the particular error-correcting code that nature uses. Now, I want to be careful here because it's easy to get carried away. These results are established rigorously only within the ADS/CFT framework, and our universe is not an anti-de Sitter spacetime. Our universe is expanding. It has a positive cosmological constant, or something that behaves like one, and that makes it a de Sitter spacetime, which has very different properties. Nobody has found a convincing de Sitter version of the holographic correspondence. That's a major gap. It's one of the biggest open problems in the field, and it's been open for over 25 years now. So, when we talk about space-time emerging from entanglement, we should remember that the strongest evidence comes from a setting that isn't quite our universe. But the ideas feel too coherent, too interconnected, to be accidents of a special case, and there are people working hard on extending them. One approach, championed by physicists like Tom Banks and Willy Fischler, tries to build a holographic framework for cosmological spacetimes directly. Another, pursued by people like Nima Arkani Hamed, takes a completely different tack, looking for mathematical structures that can describe physics without assuming spacetime exists at all, and then showing that spacetime emerges from those structures in appropriate limits. Arkani Hamid's work on the amplituhedron, and more recently the icosahedron and surfacehedron, these are geometric objects in abstract mathematical spaces that encode the outcomes of particle interactions. You don't need to know the details. The key point is that these objects calculate the same things that Feynman diagrams calculate, the probabilities of particles scattering off each other, but they do it without ever mentioning space or time. Space and time aren't inputs to the calculation. They're not assumed. And yet the answers come out right. The suggestion is that space and time are useful organizational tools, but they're not where the deepest description of physics lives. This connects to something else that's been quietly revolutionary, the role of the cosmological constant, or dark energy, which is arguably the most embarrassing unsolved problem in all of theoretical physics. Here's the setup. Quantum field theory predicts that empty space should be seething with energy. Virtual particles constantly popping in and out of existence contribute to the energy density of the vacuum. When you try to calculate how much energy the vacuum should have, you get a number. And when you compare that number to the observed value of the cosmological constant, the thing that's driving the accelerating expansion of the universe, which we've measured quite precisely since 1998, the theoretical prediction is too large by a factor of roughly 10 to the power of 120. That's not a small discrepancy. That's the worst prediction in the history of science, if you want to be dramatic about it. 120 orders of magnitude off. Now, you might think, well, maybe there's some symmetry or mechanism that cancels most of that vacuum energy and brings it down to nearly zero. And people have looked for such mechanisms. Supersymmetry was one hope. It pairs every boson with a fermion, and their vacuum energy contributions have opposite signs, so they could cancel. But supersymmetry, if it exists, is broken in our universe, and the cancellation isn't perfect. You'd still be left with a value way too large. Other approaches invoke the anthropic principle and the string theory landscape. Remember those 10 to the 500 possible vacua? Maybe each one has a different cosmological constant, and we just happen to live in one where it's small enough for galaxies to form and life to evolve. Steven Weinberg actually made a rough prediction along these lines back in 1987, before the accelerating expansion was even discovered, and his predicted range turned out to be roughly correct. But many physicists find this deeply unsatisfying. It feels like giving up on explanation. It feels like saying the fundamental constants of nature are just accidents of our particular address in an unimaginably vast multiverse. And yet, the cosmological constant problem might be telling us something profound about quantum gravity. Because the vacuum energy calculation that gives that absurdly wrong answer assumes that quantum field theory works the way we think it does all the way down to the Planck scale. It assumes that space-time is smooth and continuous at every scale, that you can keep zooming in forever. But if space-time is emergent, if it dissolves into something else at very short distances, the way a pointillist painting dissolves into individual dots when you press your nose against it, then that calculation is simply wrong. Not wrong in its logic, but wrong in its assumptions. You'd be integrating over degrees of freedom that don't actually exist. The cosmological constant problem might not be a problem with the cosmological constant at all. It might be a problem with our understanding of what space-time is. That's a theme that keeps coming up, isn't it? The hardest problems in physics, the ones that have resisted solution for decades, might not be solvable within the current framework. They might be symptoms, signs pointing toward a deeper framework that we haven't fully grasped yet. The measurement problem in quantum mechanics, the arrow of time, the nature of space-time, the cosmological constant. They might all be connected, different faces of the same, underlying mystery. And if that's true, if these seemingly separate puzzles are really one puzzle seen from different angles, then solving any one of them might crack the others wide open. That's the hope, anyway. That's what keeps people working on this stuff late into the night. So let's pull on that thread a little more, because there's a question we've been circling around for a while now, one that sits right at the heart of everything we've been talking about. It's deceptively simple to state. What is consciousness, and does physics have anything to say about it? Now, I want to be careful here. This is a topic where it's very easy to slide into hand-waving and mysticism, and I don't want to do that. But it's also a topic that serious physicists and philosophers have grappled with, and it connects to the measurement problem in ways that are genuinely unresolved. So let's walk through it honestly. Here's the setup. Remember the measurement problem. The fact that quantum mechanics seems to have two completely different rules for how things evolve. When nobody's looking, a particle's wave function spreads out, explores all possibilities, evolves smoothly according to the Schrödinger equation. But when you measure it, the wave function appears to collapse. One outcome becomes real, the rest vanish. And quantum mechanics, as a theory, doesn't tell you what counts as a measurement. It doesn't draw a line between the quantum world and the classical world. That line, the so-called Heisenberg cut, has to be put in by hand. And where you put it seems, at least on the surface, to have something to do with observation, with someone looking. Eugene Wigner, one of the great mathematical physicists of the 20th century, took this very seriously. He proposed a thought experiment now known as Wigner's friend. Imagine a friend of yours is in a sealed lab measuring a quantum system, say, whether a photon is polarized horizontally or vertically. From your friend's perspective, the measurement happens, the wave function collapses, they see a definite result. Done. But from your perspective, outside the lab, your friend and the photon are both part of a larger quantum system, and until you open the door and ask what happened, the entire lab, your friend included, should be in a superposition. Your friend is simultaneously the person who saw horizontal and the person who saw vertical. That's deeply weird. And Wigner's original conclusion was that consciousness must play a role, that the wave function collapses when a conscious mind becomes aware of the result. Most physicists today don't accept that conclusion, but here's the thing. They haven't definitively ruled it out either. The measurement problem remains genuinely unsolved. The many worlds interpretation avoids it by saying the wave function never collapses, it just branches. The decoherence program explains why we don't see macroscopic superpositions in practice. Interactions with the environment scramble the interference patterns incredibly quickly. But decoherence doesn't actually solve the measurement problem. It explains why the different branches don't interfere with each other, but it doesn't explain why you experience one particular branch. It doesn't explain why there's something it's like to be you, observing this particular outcome. And that brings us to what the philosopher David Chalmers called the hard problem of consciousness. The easy problems of consciousness, and he's being a bit ironic calling them easy because they're incredibly difficult, are things like, how does the brain process information? How does it integrate sensory data? How does it direct attention, control behavior, distinguish waking from sleeping? These are problems for neuroscience, and enormous progress has been made on them. But the hard problem is different. The hard problem is, why is there subjective experience at all? Why does it feel like something to see the color red, to taste coffee, to hear a low note on a cello? You could imagine a being that processes all the same information, responds to all the same stimuli, behaves identically to you in every measurable way, but has no inner experience, no lights on inside. Philosophers call this a zombie, not the horror movie kind, but a philosophical zombie. And the hard problem is explaining why we're not zombies, why consciousness exists at all. Now, you might say, well, that's a question for neuroscience or philosophy, not physics. And maybe you're right. But there are reasons to think physics might be involved. One reason is the measurement problem we just talked about. If observation plays some fundamental role in quantum mechanics, then understanding what observation is becomes a physics question. Another reason is more subtle. It has to do with information. Remember how we talked about information becoming central to physics? How Landauer showed that erasing information has a physical cost, how black holes forced physicists to take information conservation deadly seriously, how the holographic principle suggests that information might be more fundamental than spacetime itself? Well, here's the thing about consciousness. Whatever else it is, it seems to involve information processing. It seems to involve a system that integrates information in a particular way, that models itself and its environment, that has a unified experience rather than a collection of disconnected data points. Giulio Tononi, a neuroscientist at the University of Wisconsin, developed a framework called Integrated Information Theory, IIT for short, that tries to make this precise. The core idea is that consciousness corresponds to integrated information, which he denotes with the Greek letter phi. A system has high phi when its parts are highly interconnected, when the whole system carries more information than the sum of its parts, when you can't divide it into independent pieces without losing something. Your brain has enormously high phi. A hard drive, despite storing vast amounts of data, has very low phi because its bits are largely independent of each other. You can split a hard drive's memory in half, and each half still works fine. You can't do that with a brain. What's fascinating and controversial about IIT is that it's a theory of consciousness rooted in information, and information, as we've seen, is increasingly looking like the fundamental currency of physics. If IIT is on the right track, then consciousness isn't something separate from the physical world, something sprinkled on top. It's a feature of how information is organized. And if information is what space-time is made of, if the universe at its deepest level is a network of entangled quantum information, then consciousness might be woven into the fabric of reality in ways we don't yet understand. I want to be clear. This is speculative. IIT is a serious scientific framework with testable predictions, and some of those predictions are being tested right now in neuroscience labs. But the connection to fundamental physics is still more suggestive than established. It's a direction, not a destination. And plenty of physicists and philosophers think it's the wrong direction entirely. But it's worth knowing about, because it shows how the deepest questions in physics, what is information, what is space-time, what does measurement mean, bump right up against the deepest questions about minds. There's another angle on this that's worth mentioning. Roger Penrose, the same Penrose who proved singularity theorems with Hawking, who won the Nobel Prize in 2020, has argued for decades that consciousness is fundamentally linked to quantum gravity. His argument is intricate, but the basic idea is this: human mathematical understanding involves something that can't be captured by any computational algorithm. He draws on Gödel's incompleteness theorems to argue that the mind does something that no Turing machine can do. And if that's true, then consciousness must involve physics beyond our current theories. Specifically, he thinks it involves quantum gravitational processes in structures called microtubules inside neurons. He developed this idea with the anesthesiologist Stuart Hameroff, and it's called orchestrated objective reduction, or ORC-OR. Most neuroscientists are skeptical. The brain is warm and wet, and quantum coherence is extremely fragile. It's hard to see how it could be maintained long enough to matter in neural processing. But Penrose's deeper point is worth taking seriously, regardless of whether his specific mechanism is right. The point is that our current physics might be incomplete in ways that matter for understanding consciousness. That the hard problem might actually require new physics, not just better neuroscience. And here's where it all loops together. If consciousness is connected to quantum mechanics, and quantum mechanics is connected to information, and information is connected to spacetime, and spacetime is connected to gravity, then consciousness, quantum mechanics, information, and gravity might all be aspects of one underlying reality that we're seeing from different angles. That's not a proven statement. It's a possibility. But it's a possibility that some very serious people take seriously. Let me bring this back to something concrete for a moment. Think about artificial intelligence. In the last few years, large language models and neural networks have become astonishingly capable. They can write, reason, create art, hold conversations. And this raises a practical version of the hard problem. Are these systems conscious? Do they have inner experience? And the honest answer is, we don't know. We don't even have a good framework for answering the question. If IIT is right, then you'd need to compute the integrated information of the system, and for current AI architectures, that might actually be quite low despite their impressive outputs. But we're not sure. And as these systems become more complex, as they start to more closely mirror the information integration patterns of biological brains, this question is going to become urgent. It's not just philosophy anymore. It's an engineering question, an ethics question, a policy question. And it depends, ultimately, on physics we don't yet have. So here we are. We've traced a path from Newton's clockwork universe, through the strange probabilistic world of quantum mechanics, through the dissolution of spacetime itself into quantum information. And now we've arrived at consciousness, the one phenomenon in the universe that each of us knows directly, from the inside, and yet that physics cannot explain. There's something almost poetic about that. Physics has been extraordinarily successful at explaining the universe from the outside, forces, fields, particles, space-time geometry. But the view from the inside, the fact that there is a view from the inside, remains the deepest puzzle of all. And maybe that's exactly where we should expect to end up, if the universe is the kind of thing that can be known from the inside in the first place. Because think about what that implies. If consciousness is truly fundamental, if it's woven into the fabric of reality at the deepest level, the way some of these theories suggest, then the fact that physics can't currently account for it isn't a minor gap. It's a clue. It's telling us that our current framework, as spectacularly successful as it's been, is still missing something essential. And whatever that missing piece is, it might be the same missing piece that resolves the measurement problem, that explains why time has a direction, that tells us why the cosmological constant has the value it does, that reveals what spacetime actually is underneath. One missing piece. One deeper theory. That's the hope, anyway. And, it's worth stepping back for a moment and appreciating just how far we've come in this story. Because the arc of it is genuinely remarkable. We started with Aristotle, who looked at the world and saw heavy things falling and light things rising, and said, well, that's just what they do. That's their nature. And for nearly 2,000 years, that was good enough. Then Newton came along and replaced that with something breathtaking. A universal law, a single equation that described the apple and the moon and the tides and the orbits of planets, all in one framework. And that felt like the end of the story. It felt like we'd cracked it. Kelvin stood up in 1900 and said the edifice of physics was essentially complete, just two small clouds on the horizon. And those two small clouds turned into relativity and quantum mechanics, which together demolished the Newtonian worldview and replaced it with something far stranger and far more powerful. And then those two revolutionary theories, each triumphant in its own domain, turned out to be incompatible with each other. General relativity and quantum mechanics, the two pillars of modern physics, cannot both be exactly right, and the effort to reconcile them has led us into territory that Newton could never have imagined. Space-time itself dissolving into quantum entanglement. Information as the fundamental currency of reality. The geometry of the universe emerging from patterns of correlation in some deeper, pre-geometric substrate. That's where we are now. That's the frontier. But here's what I find most beautiful about this whole journey. Every time physics solved a problem, the solution revealed a deeper mystery. Every answer was also a question. Newton explained gravity, but couldn't explain what gravity was. What mechanism allowed masses to attract each other across empty space? He called it action at a distance and admitted he had no hypothesis for how it worked. Einstein answered that question. Gravity is the curvature of spacetime, but his answer raised new ones. What is spacetime made of? Why does it curve the way it does? What happens at singularities where the curvature becomes infinite? Quantum mechanics explained the behavior of atoms and light with extraordinary precision, but the very framework that makes those predictions, the wave function, superposition, measurement, raises questions about the nature of reality that we still can't answer. What does it mean for something to be in two states at once? What counts as a measurement? Why does observation seem to matter? And Boltzmann explained entropy and the second law of thermodynamics using statistical mechanics, which was brilliant, genuinely one of the great intellectual achievements of the 19th century. But his explanation only works if you assume the universe started in an extraordinarily low entropy state, and nobody can explain why it did. The past hypothesis, as we talked about earlier, it's an assumption we have to make, and it works, but it's unexplained. It just sits there at the foundation of our understanding of time's arrow. This brute fact that cries out for a deeper reason. So the pattern is clear. Physics doesn't converge on final answers. It converges on better questions. And the questions we're left with now, the ones we've been exploring together tonight, they feel different from the questions of previous eras. They feel more fundamental, more interconnected, more like they might all be aspects of one question. Let me try to articulate what that one question might be. And I want to be careful here, because this is speculative territory, and I don't want to pretend there's a consensus where there isn't one. But if you look at the open problems we've discussed, the measurement problem, the arrow of time, the nature of space-time, the cosmological constant, consciousness. There's a common thread running through all of them, and it has to do with the relationship between information and reality, between the knower and the known, between the inside view and the outside view. In quantum mechanics, the measurement problem is fundamentally about what happens when information about a system becomes available to an observer. Before measurement, the system exists in superposition, multiple possibilities coexisting. After measurement, one outcome becomes real. What bridges that gap? What makes information definite? In thermodynamics, the arrow of time is about the flow of information. Entropy increases because systems evolve toward states where we have less detailed information about their microscopic arrangement. Time's direction is, in a very real sense, the direction in which information gets scrambled. In gravity, the emerging picture from quantum gravity research is that space-time itself is built from entanglement, from quantum information linking different parts of the universe. The geometry you and I experience, the 3 dimensions of space and the flow of time, might be a macroscopic manifestation of an underlying pattern of quantum correlations. And consciousness, well, consciousness is the phenomenon of there being an inside to information processing. It's what it's like to be a system that integrates and processes information in certain ways. So information keeps showing up. It's there in every one of these puzzles. And that's led some physicists and philosophers to wonder whether information is the truly fundamental thing, more fundamental than matter, more fundamental than energy, more fundamental even than space-time. John Wheeler's it from bit, the idea that every particle, every field, every force, every element of physical reality derives its existence from answers to yes or no questions, binary choices, bits of information. Now, if that's right, and again, this is a big if, then the open questions of physics aren't separate problems waiting for separate solutions. They're different faces of the same diamond. The measurement problem is asking, how does information become definite? The arrow of time is asking, why does information flow in one direction? Quantum gravity is asking, how does information give rise to space-time? And consciousness is asking, what is it like to be information? Same underlying mystery, different angles. And there's something deeply satisfying about that possibility, even if we can't prove it yet, because it would mean that the universe has a kind of unity to it, a coherence that goes beyond what we've been able to see so far. It would mean that the fragmentation of physics into separate domains, quantum mechanics over here, general relativity over there, thermodynamics in this corner, neuroscience in that one, is an artifact of our limited perspective, not a feature of reality itself. And resolving that fragmentation, finding the deeper theory that unifies all of these threads, would be the greatest achievement in the history of human understanding. Bar none. But will we get there? That's the honest question, isn't it? And the honest answer is, we don't know. There's no guarantee that the human mind is capable of understanding the deepest nature of reality. There's no law of physics that says the universe has to be comprehensible to a species of clever primates that evolved on a small rocky planet orbiting an ordinary star in an unremarkable galaxy. And yet, so far, it has been comprehensible, unreasonably so. Eugene Wigner wrote a famous essay in 1960 called The Unreasonable Effectiveness of Mathematics in the Natural Sciences, and his point was exactly this. There is no obvious reason why the universe should be describable by elegant mathematical equations, and yet it is. Newton's law of gravitation, Maxwell's equations of electromagnetism, Einstein's field equations, Dirac's equation for the electron, Schrödinger's wave equation. These are not just approximate descriptions. They are precise, beautiful, and shockingly effective. The universe seems to want to be understood. Or at least, it doesn't resist understanding the way it could. So maybe we will find that deeper theory. Maybe someone is working on it right now. Maybe it's a graduate student somewhere, scribbling on a whiteboard at 2 a.m, following a hunch that doesn't quite make sense yet, but won't let go. That's how it's always happened before. Einstein was a patent clerk. Boltzmann was an outsider whose ideas were rejected by the scientific establishment of his time. He died before his work was fully vindicated. Planck stumbled into quantum theory almost by accident, trying to fix a technical problem with blackbody radiation, and ended up launching the greatest revolution in the history of physics. The breakthroughs never come from where you expect them, and that's part of what makes this story so compelling. It's not finished. It's not a story with an ending. It's a story that's still being written, right now, by thousands of physicists and mathematicians and philosophers around the world, people who lie awake at night, thinking about these exact questions. What is spacetime made of? Why does quantum mechanics work the way it does? What is consciousness? Why is there something rather than nothing? That last one. Why is there something rather than nothing? We haven't even really touched on, and it might be the deepest question of all. But it's there, underneath everything. Leibniz asked it in 1714. Heidegger called it the fundamental question of metaphysics. And physics, for all its power, has no answer. It can describe the something in extraordinary detail: the particles, the forces, the fields, the geometry, the evolution from the Big Bang to now. But it cannot explain why there is a something to describe, why these laws and not others, why anything at all. And maybe that's okay. Maybe some questions are genuinely beyond the reach of physics, or maybe they're not. Maybe the final theory, whatever it turns out to be, will be so self-contained, so logically necessary, that it couldn't have been otherwise. That the laws of physics are the only self-consistent set of laws possible, and the universe exists because it must. Some physicists have speculated along these lines. It's a beautiful idea. Whether it's true is another matter entirely. But you don't need to solve these problems tonight. Nobody does. Tonight, these questions are just companions in the dark. They're the kind of thoughts that can actually be comforting, in a strange way, because they remind you that the universe is vaster and more mysterious than anything we've yet imagined. And that's not a failure of understanding. It's an invitation. Every unanswered question is a door that hasn't been opened yet. Every gap in our knowledge is a place where wonder still lives. So as you lie there, letting your thoughts soften and slow, consider this. You are made of atoms that were forged in the cores of ancient stars. The carbon in your bones, the oxygen in your blood, the iron in your hemoglobin. All of it was cooked up in nuclear furnaces billions of years ago, scattered across space by supernova explosions, gathered together by gravity into a new solar system, a new planet, and eventually, somehow, into you. And you are conscious. You are the universe looking at itself, wondering what it is. That's not a metaphor. That's literally what's happening. The atoms in your body are the same atoms that make up the stars, and they have organized themselves into a structure so complex that it can contemplate its own existence, ask questions about the nature of time and space and information, and feel wonder. And right now, those atoms are settling into rest. Your breathing is slowing. Your thoughts are becoming gentler, less urgent, more like drifting clouds than marching soldiers. And the questions, the beautiful, impossible, unanswered questions of physics, they'll still be there in the morning. They've been waiting for centuries. They can wait one more night. The measurement problem will still be unsolved when you wake up. The arrow of time will still point in the same direction. Spacetime will still hold you gently against the surface of this planet, curving just enough to keep you right where you are. And consciousness, your consciousness, will return after sleep as mysteriously as it always does, with no explanation for why there is something it is like to be you, but with the undeniable fact of it, warm and present and real. So let that be enough for now. Let the questions be a kind of lullaby. The universe is stranger than we know, deeper than we can currently fathom, and more beautiful for its mysteries. And you are part of it, not separate from it, not observing it from outside, but woven into its fabric, made of its stuff, shaped by its laws, asking its questions. That's a remarkable thing to be, and it's a good thought to fall asleep to.